Web Forum. So my name is Cameron Rappaport. I'm a field product manager here at AW Chesterton, and joining me is Rodney Roth. Rodney, I don't know if you want to give a little bit of your pedigree. I know you have quite a bit of experience with this.
I am the global OEM manager for Lowy Valve Sealing and the strategic accounts manager as well. So 25 years in the industry and the voting member for Chesterton for API regarding these types of products.
Yep. So it's a great resource to have on hand, and you guys should hopefully take good advantage of this, because he's just a wealth of information. He's my first go-to. So, unless any of you guys have any questions, this has been as a question and answer session. You can use that chat box over there on the left. Otherwise, I have some kind of general questions, common questions we encountered that we can go over. So feel free to chime in at any time. So Rodney, I think a good place to start is, because actually, one more piece of housekeeping. Today's question and answer session is sponsored by the Fugitive Emissions Summit Americas. Fugitive Emissions Summit Americas is June 13th through the 14th down in Houston, Texas, and Rodney Roth is actually the chairman of that. So that'll be great. So when we're talking about fugitive emissions, a lot of what we talk about is LDAR, which is leak detection and repair. So, Rodney, I wanted to talk to you a little bit more about what exactly is the definition of a leak.
Well, okay, so the definition of a leak is always going to be dependent upon what the company has either defined in their own LDAR program, which are initially considered voluntary, or if they are in what is called a consent decree, where they have signed a documentation with the U.S. EPA to do things after being fined to reduce those fines. That will be called enhanced LDAR. And so what typically happens is those leak definitions drop, well, all of the enhanced LDAR 100 parts per million or less. The 10,000 is a national standard. Of course, if you're looking at the screen, you can see some of the other definitions that are there, 500 to 1,000. We're all going to be at 100 parts per million in the very near future. 70% of the refineries in the U.S. are already under some sort of a consent decree requiring this. And I was actually in two forums with the EPA yesterday at an environmental conference, and they expect to have the rest of the refineries under consent decrees within the next 12 to 18 months. So we can look at all these other numbers, but let's talk about leaks from our perspective relative to our product line as being 100 parts per million.
Yeah, so 100 parts per million, and in general, our recommendation is that even if you might have a slightly different standard, whether you're not under a consent decree, and it might be somewhere between 500, 1,000, 10,000, depending on what national standard you're using. You might have a state or local standard. But it's best practice is 100 parts per million. You're never going to have to answer any questions as to does your leak definition match the legal one if you're going with 100. So again, I can see people joining. I'll just say every once in a while, if you have any questions, you have that chat box there on the left. So the other component of LDAR that I think people have a lot of questions about is VR. So, Ronnie, if you want to talk about the repair and what that means.
Well, first of all, the R in LDAR does stand for repair, but in the world of the Environmental Protection Agency and the end users, the repair has two different definitions. So what we see there on the screen of retightening and retorquing, those are maintenance events in the eyes of an end user, and it would be a maintenance event in our eyes as well. That's how we maintain backing, or how we maintain any joint that has faults, is the first attempt to tighten them or retorque them if necessary. So actually, it is my goal, and what I presented to the EPA, that we remove the R from LDAR and we change that to a P eventually for prevention, because if valve packing gland flanges are maintained effectively, there's a good chance that the need for repair is not there. Now, there is a 5 to 15 day rule in all of these LDAR programs and in consent decrees where they must make that attempt, and in all actuality, they must make that attempt twice. And then that valve is tagged as a leaker, and then it has to monitor 2 consecutive months below the threshold required before that tag can be removed. And then if it doesn't, then it becomes a chronic leaker, and it goes on a totally different list, and then the fines start to occur. So, starting with Camden earlier before we started, the next step, if they, in all of the consent decrees, if they cannot manage the leak by retightening, they do what is called an extraordinary repair. And in our world, it's really not extraordinary. It's called a drill and tap. It's where they use a leak sealing company that actually drills in and taps and places an external fitting on, and then pumps in a pumpable packing to re-energize the stuffing box and hopefully control the leak.
Yeah, so that's a lot of time and investment between remonitoring, so you have personnel doing that, between hiring another company for drill and tap. So that, I think it's a good emphasis getting there with that P. The prevention is really going to drive down your lifetime cost of that valve.
And also, too, you have to understand that they may be on quarterly monitoring, and once it becomes a leaker, it becomes monthly monitoring. So instead of doing it every 3rd month, you're doing it 3 times a quarter.
Right. You have a lot of chronic leakers. You can drive the frequency of your monitoring more across your entire plant, right? So if you have a lot of chronic leakers, you go over a certain threshold and you were on, say, biannual or annual monitoring, that can get bumped down to quarterly or biannual. You go down that next step. Here's some other. So what are the biggest concerns for LDAR programs? So Roddy, what do you run into with people who they're having problems with their LDAR? What do they need help on the most? Answers are kind of on screen.
The biggest issue with LDAR programs is there's a tremendous amount of training for managing the leak detection. There's a tremendous amount of training on how to manage the reporting. There's a tremendous amount of training on how to manage the program, but there's little to no training on the actual repair, the R. So, again, the presentation I made on Wednesday for the 4C conference was managing the R and LDAR, and the emphasis pretty much after every other slide is that there has to be training. And so you have to train the personnel to understand all aspects. And that doesn't just mean training plant personnel. That could be training in-plant personnel, contract personnel in the plant, or also we could be training third-party repair contractors such as United Valve or Southern Valve Services or DK Image or companies around the country that are doing valve repair to ensure that they're, installing packing correctly and maintaining the stuffing box and stem to the finishes that we need so that this program can become a preventative program instead of a reactive program. We're looking at prevention instead of reaction, which, that's my other thing too, is that prevention is very positive and reaction is very negative and also extremely costly. So we need to train, and then train again.
All right. So out of curiosity, I know you do a lot of trainings for probably a lot of people who've already been packing valves for years, if not decades. What do you find is the thing that you teach them that they didn't already know?
How to use a torque wrench.
Really?
That's a simple answer. I mean, you know, people understand how to rotate the splits in the packing in most cases. Long-term guys understand there's ways to effectively resize a packing in the field if you have to use a rolling pin or something, if it's a little tight. People understand how to cut guide cuts, use different cutting devices. But the torque issue and right alongside the torque issue is the proper use of anti-seize or lubrication. So we spend a lot of time talking about 783 ACR and 772 premium anti-seizes that Chesterton provides to work in conjunction with a good training program.
Yeah, and you can see that. You know, I pulled this example valve from something you did, Rodney, where, you know, that packing gland's probably tight, but it's cocked, and that's going to be an ineffective seal. Speaking of anti-seize, how important is that? Oh,
that picture is a very interesting picture and something that can be remedied pretty easily. But I have a lot of other pictures where they actually bent the glands, and so there's no remedy for that, no replacement of the gland flange.
So over torquing as well as under torquing can both be detrimental.
Correct.
All right. So on thread lubricant and anti-seize, I know this is something that a lot of people maybe don't properly understand or don't have the whole picture on, or they don't know exactly why it gets used. I wonder if you could speak to that a little bit.
Well, the most interesting thing about anti-seize, as I've talked about it more and more over the past few years, especially with the relevance of the maintaining of low E packings, is that most people have used anti-seize in some shape, form, or fashion when they've been bolting flanges for a long time. They may not have applied it correctly. They may not have used a really good anti-seize, but they use something. But with valves, the anti-seize is much more important, and the use of quality anti-seize is exponentially more important in a valve, because valve maintenance requires continually retorquing of the gland flange studs. And so if you do not have an anti-seize that has a close spread between a wet friction factor and a dry friction factor, then no one knows how to torque those valves effectively. And so we found that the use of 783 ACR, which is our ceramic-based product, exclusively to those bolts that would be considered carbon steel, or the terminology is ferritic, has a very narrow spread between wet and dry. And so it's similarly, the loading is very similar from day 1 to day 1,000. Whereas there are a lot of other anti-seizes in the market that may have a wet friction factor of 0.15 or 0.16, which would be really low. And then when we get to the upper end, it could be twice that. It could be 0.27 to 0.32. And how do you torque that? And can the studs actually handle that additional load? So that's why it's most important. And more important in valves is because we're continually tightening valves, and we're continually adjusting the glands and the gland flanges to keep that load correct. And if we don't use anti-seize effectively, it'll never happen.
Yeah, so you talked a lot about the wet versus dry nut factor. Do you want to just give a little explanation of what you mean by that?
Yeah, well, every anti-seize has a solid content and then some sort of a liquid carrier or lubricating content, so that we can actually get it onto a bolt or a nut or a washer out of a can or a tube or even a spray. And so when it first goes on, it's wet, obviously. A little dab of 772 will paint your whole arm by the end of the day if you don't get it off. So the fact is that once that stuff starts to heat up or it starts to sit out in atmosphere, those wet lubricant components of that, the liquids or the greases or oils or whatever it's made from, depending on whose it is, those are going to dry out, and then you're going to be left with just your solids component, unless those materials that you use in there are not completely cooked out and it's not completely dry. And so you can have, I mean, I've actually seen and done testing where we've seen scatter go 3 times as high. So the original torque was calculated at a 0.16, and when we actually ran the testing, we found that it was 0.45 to 0.50. And so the actual thing is, and what I'm saying wet or dry is that when it's been sitting there for a while, it's dry. Or it's 4 years after it's installed, it's dry. And so what friction factor, and friction factor is what we use to calculate the torque, along with the size of the studs and some other information. But what friction factor do you use? And so having a product that you can understand the dry friction factor is very important to know when you're retorquing 2 or 3 years down the road that you torque to an effective number to keep the packing loaded.
All right. So Elon over in the chat box asked if 785 is just as good as 783.
Absolutely not.
There's an easy answer. Do you have any elaboration on that, or why is that?
The solids material that's actually in it. The ceramic material that's in 783 ACR, when used effectively with the ferritic bolts or the carbon steel bolts, I can't explain to you how well it works. We've been using it almost extensively and exclusively for about 1.5 years with our end users and our valve manufacturers all over the world, and we're finding just amazing results with the product, and we're just. I like 772 premium as well, but the spread on the wet versus dry is a little broader on 772 because the nickel is a softer solid, whereas the ceramic is a harder solid. And so it just gives a harder, smoother bearing surface if it gets applied effectively. That's the reason why I like 783 better. Of course, Mark Gunther would be the guy to really explain this in detail because I'm not a chemist, but I'm a pragmatist when it comes to this, and I've actually used all of them.
All right. So yeah, if you ever want to get connected with somebody who can answer that question in even more depth, you can contact me. I can give you my information. I'll put my email in the chat box at the end of this. And if anybody has any questions at all after this, or you think of something later, you can feel free to shoot me an email or give me a call. So yeah, Ron says perhaps we can have another seminar on anti-seize. I'm sure we could fill an hour about anti-seize. We'd probably fill a day.
Yeah, Cameron, we actually did an Ask the Expert article in Valve Oil Magazine just around lubrication properties, so that would probably be a good continuation of this valve sealing program.
Yeah, absolutely, and I can send that out to anybody who asks as well. Write that down. So another good place to go, kind of away from just what our products do, get a little bit more broad. So what really makes an emissions valve different than a regular valve? And I know it goes quite a bit beyond just the packing or the lubrication that you might use on it.
Yeah, so this is one of the things that's been most interesting about the work that I've been doing, have been doing personally, and then the work we've started to really zero in on as a company. And you just happen to have the picture I was talking about on the screen now. That gland is actually bent. That was perfectly flat when that valve work was started on the right hand side there. So what you see there is you see a bent gland, you see extrusion on packing, and you see embedment of the nut into the gland flange. And so those are all factors that cause leakage. Let me say it that way. And so when we are designing valves and packing sets to meet the low E requirements, we have to do things differently than has been done in the past. So I'll use a brief example to kind of help everyone understand on all three of these areas here. So first of all, on the bent gland, what we found is that many customers, because of how they buy their valves in China, they buy them by their weight, not by their size or class. And so in order to make the valves cheaper, that gland flange you see there that's bent is actually hollow on the bottom side. So that's not a solid block of steel. That's a block of steel that's approximately 1/4 of an inch thick right under the nuts, and then it's hollow all the way out to where the studs go through. And so that is a very weak component. When you start putting the load out as far as we do, that hollow portion is going to give. The second picture you see there showing extrusion, that's relative to the design criteria that has been established by the API to give people guidelines for manufacturing valves. And I'll use one size in particular. A 4-inch 300-pound gate valve has a 1-inch stem and a 1.5-inch bore. However, the standard says that the stem can be under tolerance a maximum of 14 thousandths, but requires a bore over tolerance, which we call the Y factor, of 15 thousandths. So if you made your stem to the minimum and you made your bore to the maximum, which is required, that combined difference is 29 thousandths. That's 29 thousandths of tolerance. First of all, a 1/4-inch packing that's going to seal below 100 parts per million is not going to expand radially more than about 20 thousandths. So you're not going to effectively seal. However, if you do put enough load on it, you probably wouldn't be able to move the stem, but then you would see the extrusion factors that we see where the gland actually went into the packing and created that extrusion. The third thing you see there is the nut embedment, and that could be due to a soft material, or that could just be due to how they actually machine the concave in there. That's an easy fix with flat hardened washers like we use on flanges. Typically we don't see that embedment until we're repairing a valve, and if people don't like to replace the glands. So we would just fix that by placing a hardened washer under the nut and lubricating effectively between the nut and hardened washer, and we wouldn't have a concern there any longer.
Yeah. So I'll point out that a reason why we run into these issues specifically is one of the things we do here, and one of the things that Rodney really helps us to run is when a valve manufacturer wants to get certified low E valves, they want to pass like a 1624 or an ISO 15848-1. We do that testing and we work together with them to get there. And just so people know, I know that all of you guys, everybody's probably very familiar with valves, but you can see that, this flange is going, this drawing tool does not do what I think it does. But this valve flange is this part right here. You can see that green arrow, and you can see that they're just not aligning. So that's going to be what's actually putting that load on packing. And when Ronnie talks about low emissions packing not expanding the way other packing does, is because low emissions packing is special because it's extremely dense, because it has to be, because there are some reasonably small molecules, we're talking on the molecular level, that are trying to get through. So because it's so dense, it's going to require a lot more pressure to expand radially. When you press axially, it expands radially. It's going to require a lot more pressure, and it's not going to expand as much. So that's when we start getting into all these issues with tolerance and extrusion.
Yeah, and let's while we're here, before we move to the next one,
sure,
let's talk about terminology. So if you're talking to people or people are talking to you, just for everybody we have people that call stuff packing followers. We have people that call them, glands. You have the gland flange, which is what you see there that's bent. The gland flange sits on top of the gland. The gland is what many people have referenced as the follower for many, many years. The gland flange puts pressure on the gland, which then goes into the stubbing box and expands the packing under the load. And so we call those studs you see there the gland flange studs and nuts. And so that's the proper terminology: gland flange, gland, stuffing box, and gland flange studs and nuts. So if you hear that, you know that they're talking about the actual flange. When they say gland flange, they're talking about the pieces actually tightened to compress the gland into the packing.
Yeah, so you can maybe see it a little bit better here. Can't exactly zoom in, but it's what I was saying is that this flat part on the top that your actual studs go through, that's the gland flange. The cylindrical part that actually enters the stuffing box is the gland. Then you have your packing inside the stuffing box right there.
Yeah, and this picture actually shows it like as one piece.
Yep.
That's not standard. There are people that make one-piece glands, but the standard is those two components work independently of each other, and they have to be self-aligning. So the gland has an angled top to it, and the gland flange has a concave in it, so that when they come down, they cinch on each other effectively.
All right. So moving to another really interesting topic, and something that we've been discussing internally a lot, which is low leak valve technology in control valves, and can you achieve true low E with a control valve?
So we know we can at Chesterton when we're using our 1724 low E sets. We know we can do that. It does require the use of live load. Where we do achieve low E in gate valves and globe valves with our 1622 without the use of live load, we cannot achieve that without the live load in control valves, and thus we would not warranty it as well. So yes, low E for PTFE, those valves that would use PTFE, it's absolutely achievable, and we do warranty that as well. The interesting thing is, the sort of thing there is that that might be left to interpretation, but for many people. But I will also say it this way: there's a difference between actual process temperature and stuffing box temperature. So that 450 degrees you see there is if the packing actually got to 450 degrees. So that's something that has to be thought about and has to be considered when you're doing this. Sorry, I'm losing my phone here. We're talking about that a lot now, and we're actually doing more and more testing to prove that we might be able to take some of our products that may have been rated to 450 and put them in valves that are actually operating in process as much higher than that.
All right, yeah, and just so it's got cut off on the slide, but it says blocking agents can vola, and that's volatilize. So over 450, you're going to get some degradation of PTFE. So Ron, I don't know if you want to talk a little bit about exactly what live loading is and why people might want to use it.
Okay, well, yeah, I mean, you see the pictures there. You see a couple of devices there. The arrows pointing at those are an actual OD guide design that they're my favorite with regards to valves, because if you're torqued effectively, that top washer will be flush with the top of the actual OD guide. The stack you see on the right, which does not have the OD guide on it, those are going to be done by torque or by measurement. That's very common and very standard as well. And there are cases where you can't get the OD guide in there, but there is an ID guide inside of that other set as well. But it's just much more easier for someone who they don't have to have a torque wrench to properly load the ones with the OD guide. And so those are bell washers. Those are engineered for us. The stack height, the OD, the ID, everything's done off of measurements that are taken in the field, and the loading and the way they're set up, whether they're in series or parallel or a combination, are all part of the loading required for the specific application that our team's designing it for.
Yeah, so if you don't know the basic principle of live loading, it's that typically when you're using a bolt to load a set of packing, the thing that actually loads it is the bolt stretches. So that's really what a bolt being tight is that's that bolt stretch. In certain applications where you think you might lose that bolt stretch, we lost Rodney's video, but in certain applications where you think you might lose that bolt stretch, and especially for things like in control valves, you can use these springs to actually load it instead of the bolt, because the bolt doesn't have a lot of room. If it grows or it shrinks a little bit or loosens up a little bit, you're going to lose a lot more stretch than you would if it does so in one of these big spring stacks. So I hope that was a good answer for you guys. I also know, Rodney, right now, 622 doesn't apply to the 6D control valves. I don't know if you want to talk about where things are headed. I know you're pretty heavily involved in that.
Okay, well, first of all, you have to understand what we're talking about. So there is no API test standard in the works or on the horizon for testing control valves. 6D is a part of 6A, which is a midstream and upstream design. Those are pipeline valves. Those may or may not be actuated. However, there is the testing in ISO 15848-1, and there is FCI testing that can be used to test control valves. However, now to answer the question, 624 only applies to rising stem valves, or rising and rotating stem valves that use graphite packing. So that's gates and globes. That's it. And if they don't use graphite packing, it doesn't apply to them. The standards that applies to currently are 600 and 602, which it's actually written in and required. And when API 623 and 603 are republished, it'll be required in those. Those valves are already in the standard to be tested. 623 is for globe valves. 603 is for thin wall body alloy valves. 600 is what is considered the CAS valve standard, and 602 is the compact port valve standard. So the 624 does not apply to anything other than 600 and 602 by specification today, but it can be used to validate other stuff. So if your graphite packing is working in a globe valve, which rises and rotates, there's a pretty good chance if you put it in a plug valve, which is API 599, which just rotates and doesn't rise, it's going to work very well. Same thing if you put it into a ball valve, which just turns quarter turn. As long as you have enough depth to get enough rings in there, most often it's going to seal very well. And we're working on 641, which is a quarter turn standard for graphite packing as well. And there'll be other standards that come out. The control valves are not, we never talk about control valves because people usually follow the ISO standard for that because it's a valve by valve test, and there's no real industry standard manufacturing protocol for how they make control valves, so it'd be kind of hard to make a test standard.
All right. So if I'm an end user and I want a low emissions control valve, I'm going to be looking for probably that ISO 15848 testing.
Correct.
All right. If you guys want to know anything more about that, you can see the recording of my last webcast with our test engineers where we discussed in depth more of these API 622, 624, ISO 15848, and the German TA Luft standards, which are all of the kind of the global, the most widely used and accepted low emissions valve and valve packing test standards. So that covers a lot of the what we have for on the slides. Again, if anybody has any other questions, you can go over on the left. I have some other questions that I've collected. One interesting one, and something that we get from customers pretty frequently, which is API 622 and 624 are done at 500 degrees. Process temperatures can be much higher than 500 degrees. So why are the standards designed relatively low when process temperatures can go much higher? And also something like the ISO standard allows for and specs in some higher temperature testing.
Well, first of all, the ISO test standard is a valve test and a valve and seal combination test. So you're not just testing the backing or the stem seal products, you're testing the valve itself in ISO 15848-1. In the API 622 test, that is a packing only test, and it's designed to be done in a fixture. It's always the same, so all the data is always comparative. Okay, so there's not a packing test on the ISO side. So if I test my packing in a Ballon valve, and someone else tests theirs in a Powell valve, and then someone tests in a Bonnie Forge valve, we could all have results, and they could all be close or different. But the reality is, they're all different because it was 3 different valves with 3 different manufacturers with 3 different designs. So you really can't compare that data effectively. So to answer the temperature question, there's 2 things. Number one, the 500 degrees was originally to be able to allow the use of methane safely. That's 600 psi, 500 degrees. You could test with methane safely. The API wanted to be able to use a hydrocarbon so that method 21 monitoring could be used to detect the leakage, so that it would be closer in line with what is being done in the field when someone is monitoring leaks in the plant. The second part of that is that if you talk to the end users, 99% of all of the processes that are quote-unquote fugitive emission processes are somewhere in the maximum temperature of those is somewhere 650 or below, and most of them are below 500. So everybody agreed that because those temperatures were low, it wasn't going to matter anyway. But as I stated earlier, I know for a fact, and we've done some testing in the Chesterton lab, where you can have an 800-degree process flow temperature and you can have a stuffing box temperature of 400, because the process does not enter the stuffing box. It's radiant heat that goes from the bottom portion of the valve and radiates up through the valve into the stuffing box. Additionally, depending on the process that it is, some materials are very good at heating stuff up, and some of them are very bad at carrying heat. So if you've got a Dow-therm product, which is a heating oil, it's probably going to heat the valve up very quickly and very evenly. But there are other processes, even water is one of them, that doesn't do very well. So because it's going to transition to a gas itself. So we have no issues with that. But if someone really, we rate our packing at 750 degrees Fahrenheit because we've actually performed the ISO testing at that temperature and been successful. But other people only rate theirs to 600 or 650 anyway, because almost every low heat product is going to have some limiting factor, but all of us have PTFE. So it's just a common place to look at it that way. But don't be real concerned about the temperature, because there are also ways to make your product effective at higher temperatures by engineering specific additions to the stuffing box to support higher temperature ratings.
All right. So another thing that people might ask is, say if something's rated to 500 psi and 750 degrees Fahrenheit, is it going to perform low E at its the maximum rated temperatures and pressures? Well,
we've performed below 100 parts per million at 1,500 degrees psi. 1,500 psi and 750 degrees. Thus, that's the top end of our 1622 warranty. Reality is, we typically never see. I never see those applications, because the other side of that is that who's going to go out and stick a future emission probe on a valve that the stuffing box is at 800 degrees? That the EPA would allow them to put that on a difficult to monitor list, or unsafe to monitor list, and we would never need it to be low E anyway.
All right. So you mentioned why methane was chosen. So I guess I'll just reiterate that briefly, because people do ask about methane, because ISO's original test media was helium, and the European standard, the German standard TA Luft, also uses helium, and API uses methane, and ISO has recently adopted the addition of methane because it is more like what you see in the field. So that's why. So Rodney, I know outside of oil and more getting into the gas industry, especially with there's new methane regulations coming out from the EPA, people are using more optical gas imaging. So they're using more OGI. Do you see that as becoming a larger part of LDAR as that technology develops, or as these the LDAR expands outside of just the oil industry and starts getting into the natural gas, into methane?
Well, the use of the OGI technology is not ever going to become a integral part of the LDAR programs, because the best OGI technicians in the world cannot see below about 450 parts per million, and so it's really cool if the EPA needs to set up fence line monitoring to see if someone's emitting large volumes of gas where they have a reason to go in and perform an audit, or if you're doing a flyover of a gas facility in the middle of the cornfields of Nebraska, and you can't drive in there, you can fly a drone in there with a camera and look. But the reality is the correlation, no one's able to correlate those leaks below 400, 450 parts per million, and that's if everything in the atmosphere is perfect and then it's taking the picture. So there's a lot of issues with OGI on the lower end of the leakage levels, and they have their place, but they're better to pick up, just point at one unit and say, okay, this unit's exceeding their limit, let's go find out why. But you can't point it at one valve and say that's 105 ppm. It can't be done.
Yeah. I know that there's more people who are trying to get into quantitative OGI now, as opposed to qualitative, but it's a very new technology, and it'll probably be a while till that can, or if it can ever really replace something like Method 21 monitoring.
No, it'll never replace Method 21 unless somebody comes up with a handheld camera that a guy can point at each valve individually and say, okay, well, I mean, they're doing quantitative now. Let me rephrase that. They're using cameras for to find quantity of leak. So they pointed at a refinery and they're going, okay, these guys' limit is X and they're emitting Y. But that only tells them that the refinery as a whole is emitting that, right? They don't know what component or components are causing that emission, because it's incapable of finding, except for mass leakers. Because if you're focusing over background, okay, so if your background reading is a perfect 100, then you can go up to 105 parts per million before you're considered to have busted up 100 ppm leak definition. Well, it can't see that. So, if somebody's at 1,000 ppm, the camera's fine. But it's not ever going to replace the handheld monitoring device until it becomes where anybody, not some super high-tech guy who's been doing it for 30 years. I talked to some very, very amazing camera guys, and I've been told the best guy in the world can't see below 400 to 450, no matter how hard he tries.
All right. So I think that pretty well covers the questions that I have for you, Rodney. If anybody else thinks of them in the last couple minutes while we wrap up here, again, feel free to use that chat box over on your left